Okay, we'll continue with the Laplace transform. Here's what it meant. Let's keep looking at properties and pairs. We already did a few here. First, notice that it's a linear transformation. That is, if I put a linear combinations of time functions here, that means this. If you go through it, you just get the same linear combinations of their corresponding Laplace transforms. And get into one way how we can use that property. First, let's look at, well, here's an Euler's formula. It relates e to the I something to cosines and sines. I don't expect you to have this memorized, but you've probably seen it someplace. So if we wanted the Laplace transform of this thing on the right, that's the Laplace transform of IKT. And we already found that e to the AT was 1 over S minus A. Here, A is IK. We don't like complex terms in the denominator. Get rid of them by multiplying numerator and denominator by the complex conjugate, like here. Then this denominator becomes S squared plus K squared, and there's the corresponding numerator. Now, by that linearity property, the Laplace transform of this little combination here is this combination of Laplace transform. We have that on the left, and this stuff on the right. We'll break this up into the real part and the imaginary part. Now we equate real to real and imaginary to imaginary. Have the Laplace transforms of cosine and sine. Here are two more pairs we would put in a table. We don't want to redo this every time. We could have derived these same results by other means, but I kind of like this one. We could have directly put cosine of KT in the integral formula, and it would have got not that easy to take integral. So far I keep talking about a table. Just with what we've done in a few charts, we've got the start of a table of transform pairs and properties. Keep going on this and get a more expansive table. And almost, I believe, any textbook that covers the Laplace transform is going to have a table of transforms in it. So you'd be working with that more extensive table. Let's say that's the only table we had so far, and we were asked to find the Laplace transforms of these guys, AT sine KT and E cosine KT. What are they? Well, remember we have the property. It's on the previous page. If you multiply the function by E AT, it's the Laplace transform. Original function evaluated at S minus A instead of S. This is this Laplace transform where I evaluated it at S minus A. And the Laplace transform sine is 3 over S squared plus K squared. So now we evaluate it at S minus A instead of S, we get this. The same thing with the cosine, we get this. And these are not just nice to haves. These functions turn up a lot as part of the solution to second order differential equations that result in oscillation of something. It happens in a lot of physical systems. So these just aren't math entities that we're doing just for the sake of math. They come up in modeling physical systems. So yeah, you can get a more extensive table, and in fact, this is an abbreviated table. It gives you some idea of other Laplace transform pairs and properties. So the idea is you would have this table as you do many Laplace. Well, those are Laplace transforms. Talk about inverse transforms. If I take anything on the right here, or at least any of these pairs on the right, I can consider the left side as the inverse Laplace transform of what's over here on the right. Like, here's a few cases. So we now work, we work on the big F of S Laplace function. We work on it with an inverse Laplace transform, and we get the time function. So the inverse Laplace transform of 1 over S is 1, etc. All these things we did in the other direction, we can now go from the S domain to the time domain. There's actually a formula for that inverse Laplace transform. It's a contour integral that requires complex variables. We don't use it at all. What we do is we'll try to break our S function up into terms that are already in the table. And then by the linearity property, transform that combination of such things into a combination of key functions, time domain functions. Here's some simple cases. Say you had this guy. Well, the table says you've got a k here and a k squared there. So what you want up here in the numerator is the square root of what's down here in the denominator. So I'll multiply and divide by the same number. This part's in the table. Here's the Laplace transform, or the inverse Laplace transform. How about this guy? Well, the first part I can express this way, and this is in the table. You got to kind of know what's in the table to do this. And over here, I have 6 over s squared plus 4. I'll put the 6 out to the left. What I want in the numerator is the square root of this guy. So I'll multiply and divide by the same number again. So now I have a 3 out here. So there's the inverse Laplace transform. Now say you have this. Well, I can break it up. And I can pull out certain coefficients. And what I want in the numerator is, let's see, whatever number is 1 less than this exponent, it's factorial. I think I have a typo here. Oh, no, I don't. Here it is. So there's s to the 1, there's s squared. So 2 minus 1 is 1, 1 factorial is 1. Good there. 3 minus 1 is 2, 2 factorial is 2. I had a 5 here. I'm multiplying and dividing by 2 again, and I have a 5 halves. Anyway, get used to things like that. And these are the simple cases. I'll leave this for another recording, but for the more usual case, you have to do what we call partial fraction expansion. And it's a little bit tedious. I kind of equate it to long division. It's a method you use. It's not fun. And we'll go through this technique in another recording. So now we're in inverse Laplace.